Hi children, now we come to a very important topic about why integral calculus is needed right from class 11, 12, even in class 9 and 10. There are some problems in which integral calculus is needed, but no one seems to have explained why we need it. Actually, some concept of integral calculus should have been there for the proper understanding of the problem. See here, this is the Earth, and then we want to know the potential at A. So what we do, M is the mass of this, so mg is the force, and then mg into distance, mg into the height will be mgh, so the potential here is mgh. This is simple. Why? Because the gravity of the earth is almost constant for some kilometer. So we have every right to put mg to be constant, the force to be constant. So the potential is mgh. But now here, when we come to a charge, we are dealing with nanometer or say 0.1 centimeter, the sphere. So 1.1 centimeter of the area of the field, the radius of the field of the charge. And here now we want to find the potential at A. Okay. How to do that? We need to know the force. So the force is Q into 1 because 1 is the unit charge divided by r square. See, this is the definition of electrostatic potential. It is the work done in bringing a unit positive charge from infinity to the point of concern. And it is so sad also that no one seems to explain infinity to our dear children. Infinity, some children or even the grown-up also who are in BSc, they thought infinity is say 10 kilometer or 10,000 kilometer. It is not so. It may be 1 nanometer, it may be 1 millimeter. Infinity means somewhere here where the force of repulsion of this charge at this point no longer exists. It is just like in the Earth, the escape velocity, the area where g no longer exists, so that is infinity. The infinity is not 10,000 kilometer. It may be 1 millimeter, 1 nanometer, which means the force at that point no longer exists and we call infinity. So now we have to do this. What is the potential? So we need to know the force. The force is Q into 1 by r square. See, Q by r square. Now when it is here, I want to move it against the charge. I have to do the work. But now when I reach here, it is no longer r. It is much reduced. When I reach here, it is very small r, smaller and smaller. So what I do, the work done will be q by r1 square dr1 plus q by r2 square dr2, q by r3 square dr3, so on and so forth. Last one, q by rn square, then drn. And in mathematics, this is known as summation from 1 to n, q by rn drn. And here comes the beauty of integral calculus. You will be doing it when you reach BSc in a nice way. So finally, the work is q by r squared dr. Instead of the summation sign, you get the integral calculus sign from infinity to r. And remember, you don't need to worry. This is a standard integral. So q is constant. The integration of 1 by r square is same as 1 by x square dx. So this is 1 by r square dr is simply 1 by r. This one you will know later on. But remember, you can memorize this as standard integral in physics. So this is how we got that the potential at A is q by r. So now we'll come to, see you have seen here, this is the limit, 1 by r, infinity through, you get q by r. This integral also, you will find it in dipole moment. We will do it in detail about the torque. The torque needed to bring the dipole to uncle theta, because when you put the dipole north-south in a magnetic field, the magnetic needle will always align along this direction. Now you need some torque to rotate it, and you'll find, I will be doing with you also, the torque needed to twist this dipole by uncle theta is twice LMH sine theta. So this one you will do, I'll show you the detail of this. So now we don't need to do this too much now. So twice LMH sine theta. Now I want to find what is the work done in bringing this dipole from 0 to this angle. So here this integral calculus will come. The work done is 0 to theta twice LMH sine theta d theta. And this one, integration, you will learn it, I'll show you. Because see, twice LMH sine theta is the torque. So if I rotate it by d theta, just like f dx, but here that is linear. But here there is rotation, so sine theta d theta is the work done. And the integration of this, 2 LMH, they are all constant. You take them 2 LMH constant. And integration of sine theta, it is also a standard integral. You will do it in your higher classes. So this will be minus cos theta, 0 to theta. So it is finally minus twice LMH cos theta minus 1. This is the work done, and that work done is stored in the energy of this dipole. This work done, you have to do work, and this is the energy. So that is something about integral calculus. And next time also I'll touch on differential calculus we encounter in physics. So for the time being, we'll meet next time. Good night.